since 3 goes into 3. 3 minus 3 is 0, so you get 0 minus 4. So it goes negative. And then the last one will be negative also. So now though it wraps back around, when you put in 4 mod 3, you're back to 1. Which that would continue. That's all you ever get when you mod by 3, is either a 1, a 2, or a 0. Because it's either divisible by 3 or it has a remainder 1 or 2. So 4 mod 3 has a remainder 1, so you get back to 1 squared. Oops, I forgot the minus part. Minus 2 to the 4 minus 1, so 1 squared minus 8. So I get a negative 7 there. Yeah, almost everyone had those perfectly. A couple maybe little tiny mistakes, but just want to make sure you had the mod down real well for the next quiz, since you have to use it a couple of times. Any question there? All right, so for the proof, I didn't take off for a couple of things on these. Let me show you what I was looking for, because I really wanted to translate the facts about mod and division into the equations, given that list that we've written on the board a few times with the arrows where I say facts, equations. I'm supposed to translate those so that then there's not much work to do for the actual proof. You don't have to do hardly anything if you do that. So for this one, it said for all z element of z, z mod 3 is equal to 1 implies z mod 3 equals 1 implies z squared plus 1 mod 3 is equal to 2. Okay, so for the assume z mod 3 equals 1 turns into the equation that z equals 3k plus 1. Pretty straightforward there. Most people have that one. Plus, for the show, now remember this one, the reason I do assume on that, I wrote down the first half of the implies the p part, because it said use a direct proof. So you're supposed to, direct proof means assume p to show q. That's what a direct proof is. Okay. So for the show, you are supposed to write down the equation for q. So for that one, it's just that z squared plus 1 equals 3. Now, I don't want to use the same letter again. You could even use the word integer if you want, but I'll use a letter since people seem to be doing that. So use a different letter, 3m plus 2. It's some m element of the integers. So you're going to figure out what that is by doing the actual proof steps. So for the proof, you're supposed to start on one side of the show. So start on the left-hand side of the show, z squared plus 1 equal 2. And then you do substitution in algebra to get to the right-hand side of the show. Trying to show the show. So we start on one side, equal, get to the other side. So first off, I can substitute in the 3k plus 1. Oops. 3k plus 1 squared plus 1. And that just boils out to 9k squared plus 6k plus 1 plus 1. And then you can pull out a 3 from the first two parts, and then the second you just add 1 plus 1. So you get 3 times 3k squared plus 2k plus 2. 2 is, at the end, is just 1 plus 1. And that's finished, because that is 3 times m plus 2. So that's what I was looking for. And you can point out that you found m if you want, but you don't have to. Pretty much done. It's done right there. So I saw a few people did slightly different things that were okay. I didn't take off for. Like, some people worked on this show equation by maybe subtracting 2 from both sides, and then using that instead, showing that instead. It's the same thing if you do a little bit of algebra on it. It's extra work though, you don't have to. You just substitute right in and it comes out in 2 steps, so you don't need to do anything else. What else? But you have to turn it into an algebra equation so that you can then do steps, which are algebra steps that you're allowed to do. You know, like substituting, combining like terms, FOIL, all the stuff that algebraically is valid. Any question on it? So for number 3, it was the induction one. So put true for all n z. N greater than or equal to 2 implies 5 divides 7 to the n minus 2 to the n. So for the base case, you're supposed to look at the p portion and pick out the smallest value of n that's mentioned, which is 2. And then you're supposed to show the equation that holds for the right-hand side. I was pretty relaxed about this as long as you plugged in n equals 2, since that's what was given here. That's what's in p, and greater than or equal to 2. So what you do is plug it in there, 7 to the 2 minus 2 to the 2. And that's 49 minus 4, so it's equal to 45, which is equal to 5 times 9. And that's what I was really looking for. You can do some of that in your head. But if you didn't turn it into an equation and you just wrote that 5 divides 45, that would be okay too. On the base case, it wasn't too biggie. So for the induction assumption, it said induction on this one. You had to use that. That's when you're allowed to, or when you're supposed to put in n equals k. So that means you don't get to use k for your other letter, but that's all right. So you assume that 7 to the k minus 2 to the k equals 5 times something. Yeah. So I did turn it into an equation there. If you wanted to do some work on the side and say 5 divides 7 to the k minus 2 to the k with the division bar, that's okay. That would be all right. That's why I wrote this. It's 5 divides 7 to the k minus 2 to the k. But you have to turn it into this because it needs an equation. So it's all right to do some side work where you just repeat q with 7 to the k. But then you have to turn q into an equation with 7 to with the k. So that's what you had to have eventually, is that. Then the show is exactly the same thing with n equals k plus 1. So 7 to the k plus 1 minus 2 to the k plus 1 equals 5 times. Now, not exactly the same thing because you can't use m again. Now, some people did, and I didn't count off. I just crossed out your m there, like just to make a little reminder. You gotta use something else. You could use integer, the word, or p. So some people did write m there and then did all the work correctly. So I didn't take off any points this time. Next time I would. But unfortunately, sometimes if you use m in the second one as well as the first one, like use the same letter twice, then it messed up the rest of the problem because if you're doing algebra on it, you look back up there and you realize, oh, well that means I could just write and start setting things equal that aren't. If you say this is equal to 5m, then you can write 7 to the k minus 2 to the k equals 7 to the k plus 1 minus 2 to the k plus 1 and start canceling stuff. But it's as long as then you might have missed a point. But I didn't take off just for saying equals 5m. Yeah, so this is some p element of z that you're trying to find. All right. So then the proof here would be the steps. I gave you some good hints on. 7 to the k plus 1 minus 2 to the k plus 1. You start on the left-hand side of that, and then work until you get to the right-hand side, which will just look like 5 times parentheses. So it's 7 to the k times 7 minus 2 to the k times 2. There were some alternatives here. I saw a few people who, instead of doing the steps that I hinted at, they did something that worked also, which is to go back to the assume, add the 2 to the k over here, and then you can just plug in for 7 to the k. Or I guess you could do that with subtracting the 7 to the k over as well. The one I did was maybe a little more complicated actually, but it works. I'll just show it again. Turn the 7 into 5 plus 2. And then same thing as 7. Then multiply through. So 7 to the k times 5 plus 7 to the k times 2. And then factor the 2 out of the second 2 pieces. Oh, I'll have to write it over here. So 7 to the k times 5 plus 2 times 7 to the k minus 2 to the k. And then I substituted 5m. 7 to the k times 5 plus 2 times 5m. And now there's a 5 in both pieces, so you can just factor 5 out again. Or factor 5 out now. 2, 10. That's what we were looking for. Being able to pull a 5 out. So the p is 7 to the k plus 2m. You could call that the p if you want, that we were looking for, whatever that integer was. Any questions on those? Great, so we'll definitely be looking at those again when it's time to review for the next test. I really don't want them to turn into like too hard of a problem. So the algebra part of it won't be anything unusual on the test. I'll make sure I repeat the same kind of algebra that you did on a quiz. But the part that you have to like just have memorized is when it says direct proof. That means you assume an equation for P and show an equation for Q, and so on. So we'll have to review that a bunch for the test. Remember which one is which. Direct, contrapositive, inductive, contradiction. Yeah.
Do you know when our next test is?
Oh yeah, I know. I need to figure that out. It's before Thanksgiving, but so it's in about three weeks from now, I guess. I had to look at the calendar again. Yeah. Nope, I meant to do that before I came in today, but I haven't yet. We've got some time still. So don't get too worried about it yet, but I do need to let you know. Probably that'll remind me and I'll do it tomorrow. For tomorrow. I think I know which day it is, but I have to double check. Okay, so any question on this? Oh, how about the new quiz? We've done a couple examples of each kind of the encryption and decryption with A through Z and binary. It's all pretty straightforward, I think, now that we've done examples of all of them. But has anybody tried it yet and get stuck on something? Need any hints? Maybe no, you haven't. So I could leave that up for tomorrow too to see if you need any hints. I've done enough examples of each kind of this that you have like 3 of each. So that means time to go on to chapter 6. immersion and the application of code and crypto. Alright, so chapter 6 is set theory. Alright, we have already talked about sets, just because we needed them in some of our implications. So, you'll see some of the same exact examples of lists of numbers in set theory. We just need to talk about how to work with them. So we'll do Venn diagrams, combining sets in different ways. And we'll do counting of sets, which involves figuring out how many elements or how many items are in a set when it gets complicated, of course. And that's super useful though, because it lets you figure out how complex an algorithm is. You gotta worry about how many things you're gonna have to do this process on, and then that'll turn in, be able to tell you how many steps you'll have to take. So, it'll be useful for complexity calculations in chapter 9, which is called combinatorics. But for now, we're just going to do the sets. We're going to do the notation for that. All right. So it is going to be a bit of review at first. The definition is a finite set. I'll call it S here. Is a collection of items, but we're going to call them elements. The only important thing about it is that you have to be has to be well defined. You have to be able to tell if an element is in it or not. So, first of all, the elements can be anything that you see in the math of the world. So, some examples are going to be numbers, lots of examples of numbers. Symbols, which often use symbols for variables, right? You can have more complicated stuff like, we could have sequences. Like a function that gives you the outputs. Or you can have sets. A set can be an element of another set, etc. As long as it's well defined. Membership in the set is well defined, which means it's not impossible to determine whether something is a member or not. You can decide membership for anything. You can decide whether anything is a member or not. Yeah, that's what I mean by well-defined. It has to be decidable. So for some examples, the examples that we've seen before are just lists of numbers. And then more interesting examples have stuff that aren't just numbers in them. And we can see some examples that are bad examples, like things that aren't sets, where you can try to define it, but it doesn't work out. It's not clear. All right, so here's a set of list of numbers like 1, 9, 17, 2, 5. So that's you read that with the curly brackets as S is equal to the set of, and then list the numbers 1, 9, 17, 2, and 5. We've actually said that before, so this is a similar example to the ones that we've had in previous quizzes, so I don't need to write that again. You could say 9 is an element of S. That's the symbol for element of, which obviously we've been using that for the proofs, like N is an element of Z. So, a little bit of review there. Note that that order doesn't matter. What I mean by that is, when you're talking about a set, it's not the list of the numbers is in no particular order. So S is also equal to, rearrange them any way you want. 2, 5, 17, 1, 9. Make sure you have everything in there. That's a 17. Also note that everything is listed only once. You can't list duplicate elements. If you do that, it's a little confusing. It could be that you're just redundant and you're saying that 5 is in there and you forgot that you already mentioned it, and then you're saying it's in there again. But there is something called a multi-set that we're going to do where you want to count things up with duplicates. No duplicate elements in the set. We'll do multi-sets next. Because sometimes you do want duplicate elements for computer programming applications, but for a regular set, there's no duplicates. So here's some more examples. This S here could have set 3, some symbols like Q, X, and the set 3, 2. So I just said no duplicate elements, but it's okay if the 3 is inside of a smaller set, because the elements of that one are just the top level, 3QX, and the set of 3 and 2. So since 3 and 2 are in like their own little container, there's no duplication of elements there. The elements are only the top level. For instance, here you would say 3 is an element of S. That's true. Also, 3, 2 is an element of S. Both of those are true statements. Just to be clear, that's a true statement. That's a true statement. But 2 is not an element of S. If you wrote 2 as an element of S, that would be false. Instead, you could write 2 is not an element of S would be true. Because even though 2 is written there, it's inside of that little one. So that container is now an element. So that's when it gets interesting, when they're nested like that. And it also makes it so that you have to be careful when you say how many things are in this. The answer would be that there's 4 elements in there. So that brings up the notation for counting the number of items in a collection, or in a set. You write it with like absolute value. So notation. Absolute value of S means the number of elements in S. So it looks looks like absolute value, but you don't actually, no one says absolute value. They say instead it stands for the cardinality. It's called the cardinality of S. So for instance, in number 2, or example 2 there, the number of items in S is equal to 4, number of elements. Even though if you look across the top, you count 1, 2, 3, 4, 5 things, and one of those is a set of its own. So the only things that you count are the actual elements, the top level elements. Only count the top level elements. Let's see some more examples. Let's do, I'll call it something else for once. T is equal to number 1, the set of the number 1, the set of the number 1, and the set of the number 1. That's good. So, you might look at that and think either it has only one thing in it, because it just has 1, or you could say it has 4 copies of 1. But actually, how many things does it have in it? You look at the top level, and after the first curly bracket, the list starts with this one, and then that one. So the cardinality is 3. It only has 3 elements at the top level. It has, you can have lots of nesting going on, but the cardinality only counts what's the first list. For another example, you could have S equals 1, 5, and S and 7. So in that one, it contains a copy of itself as an element. So it includes itself as an element. S is an element of S. And that's fine, based on the definition. All I have to do is be able to decide whether something is in there or not. 1 is in there, 5 is in there, 7 is in there, and S is in there. Anything else is not. So you can say S is an element of S here. And if you want to count how many items are in it, there's 4, because that's the top level. Even though if you tried to draw it with all curly brackets, you would never stop, because when you try to draw S itself as curly brackets, you would start over with 1, 5, S, and 7, and then you would replace S with 1, 5, S, and 7 forever. It's infinitely nested, but it's just a finite set with 4 items. Okay, so that is a little bit weird. It's got a little more recursion than you might want to deal with like in a computer program. So one thing that early on people thought might be a good idea is to rule that out and say, let's work with the set of all finite sets, or the set of all sets, I guess. You shouldn't restrict it to just finite here. You might want the integers, for instance. I should note that if you put like the integers inside of the cardinality, that is infinity. have an infinite number of them. Also has a special number, I think you call it omega, but I'm trying to remember. Good enough infinity for us. So, let me put the word maybe here. Maybe we might want to define this set. A equals the set of all sets that don't include themselves as elements. Right, to try to rule out that example down at the bottom there. So I put the word maybe there on purpose because that's what people just thought might be a good idea, but quickly realized that it runs into problems. Like you try to say the set of all sets that don't include themselves as elements, it turns out that that capital A can't be a set logically. The problem is, like, A would be, A seems like it would be fine. It would be the set of, and, well, you could put things in there like the set of 1 and 2, and maybe just the set of 1, that's fine. But then after a while, like, you definitely wouldn't put that S. That S would not be in there. The one that has S as its own element, that would not go. So sets that don't include themselves as elements. So here's the thing. What about A? You could put A in there, but that's a problem. First of all, if I put A in there, then A includes itself. It's a problem. Is A an element of A? Here's why that's a problem. If A is an element of A, put it in the list, then that means A includes itself as an element, but it's the set of all sets that don't include itself as an element. So you say, if A is in that list, then you definitely have to throw it out. A can't be in that list. But if A is not in the list of itself, of A, you wanted the set of all sets that don't include themselves. So if A is not in A, then it should be there. It turns into nonsense. Basically, you contradict yourself no matter either way. So, trying to write down A element of A as a true or false statement is impossible. If it's true, then it's false. If it's false, then it's true. So it turns into that example of a non-statement. Way back when we were describing statements have to be either true or false. Sets have to be well defined. That they have to you have to be able to decide whether something's in it or not. And if you just try to describe a set of all sets that don't include themselves as elements, then you can't. It turns into statements that are not true or false about elements that might be in there. So the conclusion is A is not a set. Find a definition for the well-definedness of it. That's the only example, actually, that I know of that's not a set. Anything else that you define, you can decide. There's probably something else. I'm just saying off the top of my head, that's the only one I know of. Or you could, if I made up another one, it would probably turn out to be the same kind of thing, where you refer to itself and then it turns into a contradiction. You can't decide. So that's mostly for your information here. Not on the test. It's the example of why you have to say that in the first place about being well defined. You have to make sure that it actually has members that are in or out. Alright, so next up is set operations. So the counting one, deciding how many things are in it, is a set operation. It takes a set and gives you a number. But then there's the operations that take two sets and give you a new set. That's the kind of thing out here. So these are going to be kind of reviewed probably for a lot of time. There's going to be union and intersection. There's all the stuff you can draw with Venn diagrams. And then plus a few others. So I'll take two sets A and B, not that set A. That one's not a set. These are two actual sets, A and B, and get new ones. I want one more example that's a bigger set that both A and B are in. So it's something that you're usually given. It's basically so that you can draw the Venn diagram. It's a bigger set U that contains both A and B. So for an example, let's say A is equal to 3, 5, Q, 1, and 12. Then B, I'll make it have 4, Q, 5, 7, and X. And then let me get a bigger set U. This U usually stands for universe. And I write it as a script because I'm going to use union as a symbol, and the union symbol looks like a capital U too. So I use a script one for this one. So this one I needed to, it's another given, but I'll just make sure that it has everything that's in both of these plus some more stuff like, let's see, it's got 9, 0, but also 1, Q, 5, 4, 7, X, 12. Make sure that I didn't leave anything out. Oh, oops, I left out the 3. I wanted a big one that has both of the little ones in it. Yeah, that's everything. Yeah. All right, so first operation is the union. So A union B looks like this. You write it, or you say it out loud as union. And it means all of the elements that are in either A or B. Now, it's not exclusive OR. It's all the elements in A or B, just regular OR. And so, in this case, Now, you don't have to list them as duplicates, so if there's some that are in both, you just list it once. So for this example, A union B would be, I think I was going to throw away this whole box of markers very soon. There's everything that's in A, and then everything that's in B that we didn't mention already. So you do 3, 5, Q, 1, 12, and anything we didn't mention yet would be the 4, the 7, and the X. So the picture of this is the Venn diagram, so I'll start drawing some of those. Just for ease of use later on. So usually for the Venn diagram, you put a box for the biggest set around it, which is U, and then circles for all the other sets that you wanted to look at. So I'll have A and B here, and the union will be both. So the elements that we had were, and we're going to do intersection next. So I'll mention intersection is the stuff that's in the middle. They both, A and B, both have a Q and a 5, right? So that'll be in here. And A had the 3, 1, and the 12. So this is A. Got to write it somewhere close by so you can tell which it is. And this is B. The B had the 4, 7, and X. And then there were a couple more things that were in neither, like the 9 and the 0. I think that's it. So you can put them outside here. 9, 0. And then for first off, I'll shade A union B. That's all of it. So it's everything that's in both circles, or in either circle. That's what I mean. So shade them both. And then the intersection would be just the portion where they overlap. So they intersect. So for that, you just draw an upside down union. The wording of it is A intersect B. And it means just the elements that are in common, that are both. You can use the word and for it. So, it's the elements that are in A and in B. So A intersect B would be just those two. 5 and Q in that picture. And if you wanted to draw the picture of it, just shade in that portion. That's pretty obvious, but there's the shading. Yep, gotta finish up there. Next time we'll do the stuff like the complements and subtraction of sets. But for now, union and intersection is all I have. Anybody who came